Welcome to the second part of the course, Curves in Engineering and Architecture. This part is about curves in road safety. In this first video, we introduce a problem in road safety engineering that is solved with the help of curves. The problem is how to design comfortable and safe highways and railways. Road safety has been an important issue as long as there have been vehicles capable of high velocities. The earliest highways interlinked straight sections with circular arcs. When faster cars became available, they experienced uncomfortable and even dangerous shaking, vibrations, when passing through the transitions from straightaways to circular sections. Engineers sought solutions, and they found them in mathematics and physics. They began to use transition curves, life-saving curves. What are transition curves, and what are they useful for? When it traverses a straight section, a vehicle's direction is constant, while when it traverses a circular section, the direction tangent to its motion changes at a constant rate. In technical language, a straight line has zero curvature, while a circular arc has constant non-zero curvature that is moreover equal to the inverse of its radius. This jump in the curvature is responsible for the shaking perceived upon passing from a straight section to a circular one. The curvature measures how much a curve curves. A straight line is a curve that does not curve, so its curvature is zero. Because a very large circle looks locally almost like a straight line, when such a circle is traversed, the rate of change of the direction tangent to it is small, and so its curvature is small. On the other hand, the line tangent to a very small circle changes its direction very quickly as the circle is traversed, so the curvature of a small circle is large. The same thing can be said in other words by speaking of the radius of curvature, which is the reciprocal of the curvature, so that the radius of curvature of a circle is the circle's radius, and the radius of curvature of a straight line is infinite, as if the straight line were part of a circle of infinite radius. The jump in the value of the curvature that results upon passing from a straight section to a circular section is responsible for a jolt. The same thing happens upon passing from a circular section to a straight section, when the value of the curvature abruptly changes to zero. Another way to understand what happens is in terms of the centrifugal acceleration. This is the acceleration that one feels when passing through a curve that pushes one to the outside of the curve, in the direction opposite to the turn. For an object undergoing circular motion at a constant velocity, the centrifugal acceleration is proportional to the square of its velocity and to the curvature of the circle it traverses. If we move at constant velocity from a straight road to a circular section, the value of the curvature changes abruptly from zero to the inverse of the radius of the circular section, an abrupt change that we perceive as a jolt. Compensating for the curvature of the circular section by reducing our velocity means depending on the driver to slow down adequately. So a better way of avoiding the jolt is to adjust the curvature of the road itself. In order to obtain a smooth transition from straight to circular, there are used curves in which the curvature varies from zero to a required value in a smooth manner, taking for instance a value proportional to the distance traversed. A curve with the property that its curvature at a point of the curve is proportional to the distance moved along the curve is called a clothoid, or a Cornu spiral. These are the most commonly used transition curves in planar road design. Adequate design of transition curves is important in constructing roads and railroads that are inherently safe to use. Well-designed transition curves guarantee consistent roadways and help ensure that the behavior of the roadway conforms to the expectations and behavior of those drivers who use it.